Baik, kita sambung sesi pembelajaran kita dengan subtopik yang seterusnya iaitu Eigenvalue and Eigenvector. Seperti saya maklumkan sebelum ini, value adalah nilai dan vektor adalah direction, di mana suatu magnitude itu bergerak, sama ada positif ataupun negatif. Dan saya boleh nyatakan dekat sini eigenvalue itu adalah sebagai natural frequency ataupun value of omega, dan eigenvector adalah mode shape, sama ada kamu kena pastikan sama ada ianya positif ataupun negatif. Dan jadinya an eigenvector describe the movement of each mass. Maksudnya ianya menerangkan pergerakan, sama ada pergerakan kalau case translation ianya positif ataupun negatif, ke kiri atau ke kanan, atas atau bawah. Tapi untuk case rotational, sama ada pergerakannya mengikut jam ataupun berlawanan jam. Dan ianya pergerakannya adalah pada setiap mass, dan setiap mass, contohnya untuk case 3 degree of freedom system akan ada 3 mass, for example. So pergerakan vektor ini adalah berdasarkan pada setiap mass. Mungkin mass nombor 1 akan berbeza dengan mass nombor 2, ataupun mass nombor 2 akan berbeza dengan mass nombor 3. Kita akan buat analisis itu berdasarkan kepada mode shape. So untuk case eigenvalue and eigenvector, there is a 3 mass system as shown inside of this figure. So from this figure, as what you can see, there is a 3 mass, and this will be for example, this will be the mass number 1, mass number 2, and mass number 3. And then every mass connected with the spring. So spring indicator been given, and this is an example only. So this direction will be either up or down, and then we can conclude this system is a 3 degree of freedom system because they contain of the 3 mass and then 1 direction. So 3 multiplied by 1 equals to 3. Okay. For the system shown, there are 3 natural frequency and 3 mode shape. If the system is 3 degree of freedom system, so automatically we can assume that there will be a 3 natural frequency as well as the 3 mode shape. So the first shape is characterized by all the mass moving in phase to each other. So mode number 1 basically pergerakannya adalah mengikut kepada semua direction yang sama pada ketiga-tiga mass. Either the mass movement upwards or positive, or all the mass will be moved downward. Itu adalah untuk case mode number 1, or we can assume there is a eigenvalue or natural frequency number 1. And then we proceed with the mode number 2. Mode number 2 is eigenvalue omega 2. So basically, as what rotating element defined, omega 2 must be higher than omega 1. And then inside of the type of movement, they contain of 3 possibilities, either the x1 positive, x2 positive, or x3 is negative, or either negative x1, negative x2, and positive x3. And then either the other mode shape defined as positive x1, negative x2, and negative x3. They define for the mode number 2. And then we go for the mode number 3. Mode number 3, basically omega 3 must be higher than omega 2 and higher than omega 1. So they contain of the 2 possibilities of the mode shape, either positive x1, negative x2, or positive x3, or either negative x1, positive x2, and negative x3. So this indicator define whether the direction or the eigenvector of the mass will be varies, depend on the mode value. So we can, for example, this video shown example of 2 degree of freedom system. So looking for the how to show you the video. So basically in the video they will show you how the movement of mass depending on the degree of freedom system. Okay, never mind. This will be the video. Hopefully you can enjoy
A 1
the
degree
video.
freedom mass-spring system has one natural frequency and one vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia, or mass, and elastic, or stiffness properties of the system. A 2 degree freedom mass-spring system has two natural frequencies and two mode shapes. In the first mode shape, first frequency, the two masses move in the same direction at the same time, basically looking like a 1 degree freedom oscillator. In the second mode of vibration, the two masses oscillate in opposite directions, one going up while the other one's going down. At the very center in between the two masses is a node, a point that doesn't move at all. A 3 degree freedom mass-spring system has three natural frequencies and three mode shapes. In the first mode shape, all three masses move in the same direction at the same time, with the center mass moving slightly farther than the outer two. In the second natural mode, the center mass is stationary at a node point, while the two outside masses move with opposite phase and opposite directions. In the third natural mode shape for the 3 degree freedom system, all three masses alternate in directions or phase. The two outside masses move together and the inside middle mass moves in the opposite direction compared to the outer two. Hopefully by now you'd be able to guess that a 4 degree freedom system would have 4 natural frequencies. In the first mode, all four masses move together, the outside two slightly less amplitude than the two in the center, but the entire system moves in the same direction at the same time. In the second natural mode, there's a node at the very center of the system, and the two halves of the system, the right half and the left half, move in opposite directions. In the third mode shape, the inner two masses move in the same direction at the same time, and the outer two masses move in the same direction at the same time, but opposite the inner pair. In the fourth mode shape, every other mass oscillates at a different direction. There are three nodes, one between every masses.
Okay, so we continue with the solution of the eigenvalue problem. So eigenvalue basically is a natural frequency. So in order for you to define the eigenvalue problem, so this will be the other method instead of how you find the equation of motion, and then from the equation of motion you generate a matrix 3 by 3 and then solve for the roots to find out the natural frequency. And in this case, for example, for the eigenvalue problem, we using this particular formula to solve the eigenvalue problem. And for example, this is a mathematical approach, and lambda is defined as a 1 divided by omega 2, and k is the stiffness, m is the metric mass, and then capital X vector is a displacement, and then this will be the external excitation force. And then by multiplying this particular equation with k negative 1. And so you can get the value of lambda remain, and then K will be identity metric, and then D will be a dynamical metric, and D defined as a K negative 1 multiplied by matrix M, and then again multiply with the direction vector of displacement, and then equals to excitation force, and in this case is 0, free vibration. And so this is a definition of after the arrangement of this particular formula, and this will lambda identity matrix multiplied by x vector is equals to dynamical matrix multiplied by x vector. And so do you remember that the non-trivial solution we define as all the equation equals to 0, and then it's also defined as the characteristic determinant in order for us to find out the roots of equation, and the roots. So roots defined as a natural frequency, and because you want to find the value of omega, and then instead of you solve it manually, you either can use a numerical method to solve if the degree of freedom system is large. And for example, you are using the MATLAB and other software, for example like Excel.